So we're going to talk about advanced Spark programming from where we left off last time. Yeah, that one. Okay, question from David is data frame versus Python versus SQL. I think that's going to take some time. I started writing it, but then I realized that it is going to take a long time. So probably what I'll do is what I have done is I have broken it down into two parts. Spark data frame versus the Spark data frame versus the pandas Python pandas data frame. That is first thing that we are going to discuss, and the I think that will make more sense when we learned about Spark data frame. All right, so that Spark data frame is coming up next. So after that, we can go over that discussion. All right, that's what I have decided. So we'll go over that part after we are done with Spark data frame. All right, wonderful, wonderful. So let's get started. All right. So what we learned was that if we are having too much of shuffling operations, right? Then, like for example, the example that we discussed last time, there's a pseudo example in the slides. Here, what we were doing is we were trying to join dynamic records on a relatively static bigger data. Here, the data we had was a user subscription list, and we were checking whether the, the last few widgets a particular user has made to your website are those widgets part of the user's subscribe topics or not. Okay, so right now, so that was the case that we were talking about. We were talking about that. Okay, let me rephrase the problem that we discussed. And before that, there's a question from David. How about the min max at the same time for the temperature? All right. So that one, I think either you could drop a message at the forum. I would love to see the approach of the class, as well as you should put your solution at, and I'm hoping that most of you should be able to do that. Okay.
Actually, I would like to add on to this. There's an algorithm which you can do it. So you
Mm-hmm.
assign you take 2 pointers. You take the first pointer as the minimum and take the
Okay.
second value as the maximum, and just
Okay.
compare the first two values.
Okay.
If the first is smaller than the second value, that means your
Right, right.
minimum
So
pointer
that
is.
approach, that's a pretty smart approach. And that approach is great if you have the linear array in the memory.
Yes, yes, that's
In this
only how it
case,
works.
in this case, if the data is really big, you really cannot go over linearly over the data,
But
right?
in one pass, you'll get both. So even that's a bad approach.
Yeah, even for one pass, you have to bring the data to locally, and then
Mhm.
you have to do that. Maybe you can use those passes over the partitions, and then you might have to do, if for each partition, you can apply that pass, and then using the reduce, you can bring those values to a single place. Okay.
Yeah, that's
All,
the approach.
all right. So basically, it's about the forming the tuple of min, min, as well as the city at the same time. Okay, it's about forming that tuple. Initial value of max and min. The initial value of max should be like the smallest number, and initial value of min should be the largest number. And then you compare the values, and that's how. Okay. So, or you can say that initial value, what you do is you convert each value. Let's say that you want to find the max and min at the same time. You convert each value into into a tuple such that the same value is minimum, same value is maximum, and there is a city. Now, when you are reducing the tuples, you basically form a new tuple. You form a new tuple out of the min and max. All right. So that way you can actually do the reduce over the data. It's about I think better idea is let's take it offline. That way I will be able to devote more time and will be able to answer. So a better idea would be that let's do it over the discussion forum. Okay. And right, because there are many other bigger better topics that we need to work on. So let's take that here. I would love to answer it. Okay. All right. Great. Great. Let's get started. So last time this is what we discussed, and we discussed that when we are joining two data sets, say user data and events, we are joining these two. So there will be a lot of shuffling, right? So instead of a lot of shuffling, what we can do is we can partition the data. We can partition the data based on based on. So here, this is what was going on before. This is premature step, right? Here we are loading the data, user subscription, and then somebody is unmuted. So could you mute? Now we do the process logs. At the process logs, we are loading the events. All right, let me just see. Okay. All right. So here, what you see is right. What we were trying to do last time is we had this user subscription list. Okay, here the file name is not complete because we don't have that file yet. Here it's a pseudocode, and we are loading the user ID and user info. Then we have written this function. What this function does is every time you call it with the location of a file. Now inside this function, what we do is we are loading the data from the log file name, and then we are joining it with our user data, and afterwards we are filtering the data from the main one and using the case in order to remove in order to just match where the data type is matching. If there's somewhere null, those records will be dropped. All right. And once that is done, we are just printing the number of visits. So what we are trying to do is we are essentially joining user data and events. Now, since the data is not sorted, or you can say indexed, there's too much of shuffling between the partitions. A smarter way would be to is basically enable the partitioning. Enable the partitioning. Use cases of your magazine whereby you are trying to join the new events with your user subscription every few minutes. So you have a static data on one hand, and you have dynamic data on another hand, and you're joining the two. Okay. Now, since you're joining, therefore, there is going to be a lot of shuffling if you have not done the hashing. So that's why the hashing is required. The partitioning is required, and by default, the partitioning is based on the key of the key value pair. And say here, so this is what we are doing. So we can partition the base data using a partitioner called hash partitioner. Okay, using a partitioner called hash partitioner, and all it does is it basically breaks the data down into those many partitions. Here we are saying break it down into 100 partitions, and this is our hash partitioner. Hash partitioner basically converts the key into a number, and based on that number you can order the data. So this way, this is one of the optimization step with respect to the this is one of the optimization step with respect to the joining over Hughes data. All right.
You mean we are concatenate the user logs with means system logs?
We are not concatenating, we are joining. Joining means intersecting. Okay. So we are finding, let's say there is a user visiting your website, and what you want to find out is that what are the pages that the user is visiting, which are not part of the subscription user has done. So you would like to first find out the subscription of the user. And how would you find out the subscription of user? By joining the user with your database, right? So that's what is happening. Instead of saying where user ID is in this particular user ID, you generally join the two tables. That's what is happening here. All right. Now, when such case arises where you are joining again and again, when you are joining again and again with certain data on the basis of certain key, it's better to use a partitioner. All right. So what does a partitioner do? Partitioner reorganizes the keys of a key value RDD or pair RDD and can be applied using partition by. There are two basic partitioners which Spark provides. The first one is hash partitioner, and second one is the range partitioner. The first one is hash partitioner, and second one is range partitioner. So the hash partitioner basically implements hash-based partitioning using Java's object.hash code. What does hash code does? Every object in Scala provides a method called hash code. What does it do? It essentially represents your object as a small number. This is very much required in many cases. So when we are defining any object, a large object, we generally need to define our own hash code function, right? That job was done by the case classes that we created. So the case classes has already automatically created the hash code function for us based on all the parameters that we have passed as argument. So it does not work if the key is an array. So we have to make sure that the key should be non-array. It should be an object. So it partitions sortable record by, then there is something called range partitioner. Range partitioner partitions sortable records by range into roughly equal ranges. Okay, the ranges are predetermined by sampling. Let's say what you want to do is you have a lot of data and you would like to partition it based on range. Let's say you have the value, you know that the values of let's say you have an RDD in which the key is the age of people, right? So what you want to do is you want to automatically break it down into, say, 3 parts such that all 3 of them have equal are almost like equal values, and that should be based, the partitioning should be based on the keys value, the actual keys value. So what it does is it basically samples the whole data. Based on that sample, it figures out that what's the maximum, what's the minimum, and what is the general frequency of various records. And then it determines, and on the basis of it, it basically breaks down the RDD into partitions, and that's how it works. So basically, the range partitioner helps you order the data in the partitions, or you can say keep the data in the partitions based on a particular based on the value of the key, while hash partitioner does it based on the hash code. All right, you can also define, so you can just call any RDD based on the based on the um, you can repartition any RDD just like this. So here we are saying sc.parallelize, and here repartition by default uses hash code partitioner and partitions the RDD, right? Now you can also partition an RDD based on hash partitioner or range partitioner like this. Please notice that here in the hash partitioner, we are just saying that please break this RDD into 2 partitions based on the hash code of the key. Here we are saying break the RDD into the range partitioner by sampling this RDD. Okay. All right. So what does glom do? Glom basically merges all the key values in the single partition, and collect basically prints them. So with glom, you can figure out which keys are together, which keys are away. Okay. So all the values in the single partition, it basically brings them into a single array, and then collect basically brings them to you. So the RDD, when you say collect, will be array of arrays after glom. So if you take a look at that, you can figure out that, okay, my data is partitioned this way. So you can quickly take a look at the way let me just show you. So, okay, 9034 at e.cloudxlab.com. All right. So now you can, let's say Spark Shell I'm launching. All right. So let me just show you what it means. Also notice that we need to import both of them. All right. So let us say that, okay, so we have, let's say this RDD. Okay, first of all, I'm going to show you this sc.parallelize, and let's say it has 3 partitions. Okay, now when I say rdd.glom, what it does is it basically it merges all the records of an RDD of all the records of each partition together. So you can see there were 3 partitions: the first partition, second partition, and third partition. You can see third partition had the element from 7 to 10. That's what glom helps. Glom basically combines them into an array. Okay. So using glom, you can essentially say rdd.1, rdd1, like this. So when you say rdd1.collect, right, you'll get all the records. So each partition's value is combined together. That's what glom does. A question from RDD is, so if my RDD was physically on a file, it'll now split it into multiple files after glom. Is that your question? Or after this? So if your RDD was physically in a file, so it then depends on how many partition does it have. If you are changing the partitions and you are saving it back, there will be one file created per partition. Okay. So if you save this, this RDD1 has how many partition? 3, right? So these RDD has 3 partitions. So when you save RDD, it will be saved in 3. Okay. Glom doesn't do much. Glom basically after the glom, like here, if you check the number of partitions here are same as RDD. Okay. All right. Okay. So you can just check. You can see the RDD as well as RDD1 both have equal number of partitions. Okay. Just that when you right here, each individual partition is made up and just check one more thing, the size of both, you will get an idea. The size of the main RDD is going to be, the count of main RDD is going to have how many elements? 10, right? While the counts of elements in the second RDD is 3, equal number of partition. Okay. So basically the glom converts the whole partition into a single value, that is an array. This is just for printing purposes, nothing else. Okay. So the main logic is here when we want to partition an RDD based on hash, this is what is going to happen. So I'm going to show you something else. Okay. All right. Let me try to show you something. So let's say we have, okay, let me just define some strings. How do I go about it? Okay, let me see if we could say, all right. Okay, so let me just define where RDD equals sc.parallelize, right? And we say this is a cat which can jump a dog, right? So this is our, and we say split. Okay, so we are just creating an RDD from this string. So this RDD is having how many elements? It's having 9 elements. Okay. Now if I say collect, right? If I say collect, this is how it looks like, right? Now we need to convert this into a key value pair. So we are going to say rdd.map, and whatever it is, we are just going to say, let's say x repeat the same value, or just convert it into underscore 1. So this is our RDD1. So this is what it is. This, okay. Now, if I want to just partition it into, say, partition by, okay, so all right. Now we have to say new hash partitioner, and here we are saying divide it into, say, 3 equal partitions. Okay, and let's save it in the second partitions. So you see, RDD2 is after the partitions. Now let's take a look at what does the RDD2 looks like. So you can see here it has given us this result, why, and we are not able to figure out which one belongs to which partition. So a smarter way would be to glom it and then collect. Okay. Okay. So this is after the partition. This is after the partition. Okay. This is, okay. So what you have here is, right? So there are how many partitions? There are 3 partitions. Remove the first array. Okay. There are 3 partitions. First one this, second one this, and third one this. Now question is, why did cat, which, can, and jump came together? Okay. Why did they came together, and why did they came together? Okay. So you can just take a look at their hash code values. So let me just collect. So RDD2, right? I'll just show you the history. And so these are the things that we did. We started from here. Okay, so those who are interested in the history, some of the lines are wrong, so you'll have to figure out which lines are wrong. So here, if we say where hash code equals, let's say we just want to see what is the hash code value of each of the strings, right? So we can say this dot hash code. Okay, so if you see at c dot collect, or let me just map whatever is the value that with the hash code of the same. Let's say that's our hash codes. So, or let me just actually, this will be smarter to do. Okay. All right. Let me write the entire thing again. So what we're going to do, let's say this is the RDD that we created. Now we are, say, converting this into something like x and x dot hash code y. We want to see what were the hash code of each of the string. And then we are here partitioning the data here. Okay, so then we are going to say rdd dot glom dot collect. All right, let me just show you again. So what I'm trying to show you is here, right? So this is the result of partitioning. Okay, what did partitioning do? Partitioning brought the records together. Okay, before partitioning, this was our RDD, or you can say this was our RDD. And before partitioning, this is how it looked. Before partitioning, this is how it looked. Let me just show you what it means. Okay, let me do glom and collect. Only then we'll be able to figure out which partition had what. Okay, so here. All right, this is useful. No, there are only 3 partitions. Okay, so we are creating the 3 partitions. Here we could have actually, yeah, at this point of time, we could have just done the 3 partitions. But it has by default created some number of partitions. Okay, it has created 4 partitions. All right. So initially, before partitioning, this is how our data looked like. This is a cat. This is the hash code of this. This is the hash code of is, and so on. Right. So what is hash code? Hash code is some way we are like converting this into numbers, like ASCII code of this plus this plus this plus this, divide by some number. That's what is hash code. So here also the same thing. So what we see is that there were 4 partitions before we started doing the repartitioning. Now in the final one, there are only 3 partitions. And how did you differentiate? By using a function called glom. Okay. So rdd1 dot glom dot collect looks like this. Okay. And rdd2 dot glom dot collect looks like this. So all right. So what we have here is the RDD1 and RDD2. Okay. So this one has been converted into 3 partitions. And on what basis? The question is on what basis? The answer is very simple. The answer is you can see the values are ordered based on the hash code. Okay. They are ordered based on the hash code. All right, let me just see why this is the hash code. A question is how, okay. The question is how the hash code generated. Hash code are basically a part of the language construct. So let's say Sandeep has some hash code, okay, right? Robin would be having some hash code. So hash codes are generally generated by uh, combining the ASCII values of each character. And if it's a complex object, it is a function of all of the member variables. All right. So you can see that the values which have same hash code are brought together. Okay. And the same way. So the values which are not having same hash code, they are far away. They are in a different RDDs. All right. This is not really partitioned based on based on ordered. It's not ordered based on the hash code. Instead, it is based on something I'll show you. I think one thing we could have done here, hash code %3. Okay. I think now it'll make more sense to you. All right. This is what it means. Okay, so this would make more sense to you now. All right, I'll show you now. Okay, now if I say rdd2.collect, now it'll make more sense to you. All right, so essentially what it does is um, it brings the values which are the same hash code together. So it groups the data based on the hash code. Okay, so and how does it do that? It computes the hash code of every element divided by number of partitions, whatever partition you're doing. So this is the logic it's using. So you can see that in every partition, the hash code, remainder of hash code when it's divided by the partition is same. The first one is 0, second one is 1, third one is 2. So all it does is it groups the data, or you can say it regroups the data based on hash code. All right. Yes. All right. So basically, the way partitioning happens everywhere, this is what happens, right? So instead of saying any, mini, miny, mo, it does the hash code %3 and then puts it in the bucket. Like if you have been to NCC or an army, whereby what you do is you say, let's say we want to convert a big filing into 3 rows. So what we let them say 1, 2, 3, 1, 2, 3, 1, 2, 3 over and over. Similar way, this is what's happening here. So first one goes in first bucket, second one, third one, and so on. We divide by 3, divide by number of partition. Whatever is the remainder is the criteria for putting somebody in the bucket. All right, that's what is happening in the hash partitioner. All right. Similarly, we have range partitioner. Range partitioner, all it does is it figures out the range of data from your input data and then rearranges the values such that there are non-overlapping ranges. All right. So there are many functions that can benefit from partitioning, like co-group, group with, group by key, reduce by key, join, left join, and right join. Meaning anywhere there is a role of, there is ordering, there is data being sorted, or and if the if, if anywhere there is data sorting involved, at all those places the partitioning would help a lot, because when you are say grouping the data and the data is already partitioned based on say hash partitioner, it'll be really easy to join two values. All right. Let me just share this code with you. So this one will make it very clear that what's going on underneath. All it is doing is computing the hash code and grouping the data based on the hash code partitioner. All right. And
Hi Sandeep,
there
I have a
are,
question in
yeah,
this. Can we change the criteria of the hash function? I mean, can you modify the hash functions?
yeah, you can create your own partitioner.
Okay. Okay, thank
All
you.
right.
Because this may not be the desired one all the time,
Correct.
based on
Correct.
just the remainder.
Correct. All right.
Thank you.
Good. Now, there are many operations that can benefit
Sandeep,
from partitioning.
I have a
Yes, go
question
ahead.
here. Is it necessary to use hash partitioning? I mean, what is the advantage of?
So whenever we, let's say you have a big RDD, really huge RDD, and every time you have to join other data set with this RDD based on certain key. Now you realize that it's just like indexing you do in databases. In the same way, you do the partitioning. All right. So that makes the whole process faster.
Okay.
Okay.
So if we have like hash partitioner means you said it will create a number for an object, right? It
Yeah.
creates a number.
Yeah. Internally, only for sorting the data or arranging the data partitioning, it will generate the number. In our case, the number generation is done by the value is generated by me. But in real case, in the it will basically do the partitioning, and whatever code it has generated, it will do it internally, and that's all. Okay.
Oh, it's like an index in the like
Correct.
SQL Server.
Correct.
Okay.
Correct.
Thanks.
Sandeep, one question. This hard partitioner 2, what is the 2 meaning?
Meaning the how many partitions you're looking in the output.
In a hash partitioner.
Yeah. After this partitioning, how many partition do you want?
Oh,
Okay.
after parallelize will not do any partition. Parallelize will just
Parallelize will do the default partitioning based on certain criteria. Okay.
okay.
And let's say you are doing the hash partitioning, meaning you want to repartition your data. You realize that this data is huge and you should put in, you should order this data based on certain criteria. So a smarter thing would be to use hash partitioning or range partitioning. It's like indexing into multiple buckets. Okay. So, so basically it is up to you how many partitions do you want. General criteria is that the number of parallel cores you have, those many partitions you should generally create. Okay. The total number of cores you have in the whole network is the number of partition you should create.
And
All right.
range partitioner we have 2 to RDD.
Yes. So range partition here, you see, the same RDD on which we are calling it, we are passing the same RDD again. Okay. Why? Because range partition has to sample the RDD and then apply the partitioning. Okay. Why it has to sample? Because it needs to know what all kinds of data is there in the RDD, and on that basis it will break down the data into ranges. Okay. So based on that data, such that each partition is non-overlapping with another. All right. It's a non-overlapping ranges it creates. Okay, say the first will be like 1 2 3, second will be 4 5 6. It won't happen like first would become 1 2 4 and so on. So range partition is a good way to partition the data such that when you concatenate the result, the data should be in the order. That's when you use range partitioner. All right. It's the same RDD on which you're calling. You must pass the same RDD here because it needs to compute you need to do the sampling. All right. So these are the operations that benefit from partitioning. It's like saying that whenever we index a table, what are the functions like where, clause, joining, and so on, everything becomes faster. All right. So here you can create your own custom partitioner. Let's say you have partition 1, partition 2, partition 3. And what you want to do is you want to partition this data such that there is no overlapping partition. Although you can use the range partition for exactly same purpose. But let's say what you want is all the data that is lesser than j, all the keys that are starting with lesser than j, go to the first partition. The everything above j should go to the second partition. In that case, you could just define your own partitioner like this. Here we are defining two parts partitioner, which takes an argument called var_num partition. Although we are not caring about it, here we are returning 1 or 0, indicating whether the given key should go to first partition or 0th partition. All right, so all we are doing is we are checking if the value of the character is greater than j, then we are returning 1. Otherwise, we are returning 0. So get partition basically return either 1 or 0, and get partition get called on uh, every key. So this is for the cases if you want to generate your own partitioner. All right. So once you have done that, you can apply that partitioner by saying new two parts partitioner, and then you can break the data into two parts. So this will essentially convert it into two arrays. All right. A question from Vinta is, what is the function of override here? Since we are extending the parent partitioner, we want to override the inbuilt function of equals and hash code. Therefore, we are defining our own methods. All right. Ideally, is not required. All right. So all we are doing is we have just defined our two-part partitioner. This partitioner is basically creating the new RDD having two partitions. First partition having all the values from A to J. Second partition having all the values above J. And this is defined in this logic. Okay, so you can create your own custom partitioner using this mechanism. All right, so you could try using this particular piece of code. All right, this is how you, here I'm defining a partitioner. All right, so this is the partitioner. Let me just give you the code here. All right, and here we're defining our class. We've defined our class. All right, it says that there is alphabet partitioner. Okay, we need to change this. All right. Okay, never mind. So I think we can just remove this part. What happened in the midway? Okay, so actually, let me just try removing these. And all right. So this is perfectly okay. Then we are testing it out. Okay, so we can say y.collect. Great. So it has basically partitioned the data into those parts. Let me just see if I can edit this and share with all of you. We'll just remove these two lines. That's all.
So is this code equivalent to the hash partitioner?
What?
The partitioning which is happening in this method, right? Is it the
Yeah.
same which the hash partition does?
This is our own code. It doesn't use hash partitioner. Is that your question?
Yes, I mean, is the logic similar to what the
Yes, yes,
code?
yes. Internally, hash partitioner also will be doing this way. Okay. So we are trying to create our own partitioner. In that case, you basically use this kind of mechanism.
So
All
this
right.
will help us in faster retrieval, right? Data retrieval.
Yes, yes. So it's basically indexing generally helps you in fast data retrieval or
Yeah.
when you are again and again joining,
Mm.
right? And here we are just creating our own partitioner. All right. Great, great. So let's move on. And here we are. So this is how we create our custom partitioner. All right. Okay. So, all right. The second part of advanced programming, I think I'll take after running through the running on cluster. Okay. Because that one requires the knowledge of running on cluster. So we are interleaving that. Okay. So this is a bit of change in the schedule. So the advanced programming one, then running on cluster, then advanced programming two. After that, we'll start the Spark streaming. All right. Now let's understand how does Spark run on the cluster. All right. So have we talked about this? I think we have once talked about this, but we'll just go through it once. All right. Great. So this we have discussed earlier, right? So the Spark's runtime architecture is something we need to understand in order to work with it. So essentially, if you have multiple machines, machine one, machine two, machine three, and there is a driver, there's a driver that needs to um, all right, let me go back. So Spark basically runs on multiple machines. Here, let's say we have node one, node two, node three. On all the machines, when we are running Spark on a cluster, there would be something called driver. Driver could be on the same machine or it could be on a separate machine. All right. This driver in our case is Spark shell. And if we are running our Spark shell in the yarn mode, what it'll do is the user will interact with the driver, and the driver is the place where the main method runs. When you launch Spark Shell, you have created a driver program. Once the driver terminates, the application is finished. While running, the driver performs the following. It converts the user programs into tasks, converts the user program into tasks called units of execution. It converts the code into DAG. It converts DAG into physical execution plan. Okay. So basically, driver is the one which schedules your code's execution on individual machine. All right. So it's basically the one that takes care of breaking down your code into the parts and then scheduling those tasks on the executors. Now, the driver coordinates the scheduling of individual tasks on the executors. It schedules tasks based on the data placement, meaning where's the data, and tracks cache data and uses it to schedule future tasks. It runs Spark web interface at 4040, right? Like for me, if you take a look at the console, this one is running a Spark UI. It tries to start the Spark UI at 4040, but whatever port it gets, it'll launch it at that particular port. Let me just show you what am I trying to do here. Okay, I hope it is there. Okay, it's not there. So, all right, how can we find out the port? sc.getconf. Okay, I'll have to. Okay, so probably it'll be, let's say, e.cloudxlab.com 4040. Okay, this is, I think, somebody else. We, okay. For me, I think it's going to be 4041. Right. I think this is mine only because nobody has executed so many things. All right. Yeah. Parallelize and collect. Okay. So you can see that whatever work I'm doing right now using this UI. Okay. Please notice that whatever is the console on which you're logged in, it should be that URL. Okay, and when we start the Spark shell, I'm not restarting it because if I restart, whatever work I've done, it'll go away. Okay, so when you start in the beginning, it'll show you that the Spark UI has been started at this port. It'll try to start at 4040, then it'll try 4041 and so on. Okay, it'll try then 4042, then 4043 and so on. Okay. So here it shows whatever completed jobs we had. Okay. And you can see all of the mechanism we have. This is where the driver was started, then status succeeded, and so on. You see? And for every job, you can just click and take a look at what's going on in it. All right. Now the next one is when we do the caching, it'll show the storage. Okay. Right now the storage is empty. I'm hoping that if I say RDD1, okay, and we say cache, right? Does it update it here? Okay, RDD1 dot take. Okay, so these are the jobs it has executed. This is the storage. Now it has come. Okay, so this is that RDD that we have just cached. All right, and yes. Okay. All right, so you can see the okay. I think I'll have to better. Okay, so these are the various. You can see. You can take a look at the entire Spark. What's going on in the using the UI Spark web interface. It starts with it starts trying to run it at 4040, then it tries 4041, 4042, and so on. Okay, so the user talks to the driver talks to the resource manager. Okay, now a question from Sachin is, what is the difference between Spark runtime architecture and normal architecture? So here we are only talking about the runtime architecture, same as the architecture Spark, because Spark is mainly used for running the tasks. All right. So now what happens when we run Spark on the cluster? Right now we are running in the local mode. So we'll run it in the cluster mode very soon. So user talks to the driver talks to the resource manager. Resource manager could be either standalone, Mesos, Yarn, or it could be a fake resource manager called local resource manager. Local resource manager is what we are using right now. Now, this component is called cluster manager. It allows, it is basically a pluggable component. So people can write their own pluggable component and hook into it. So it allows Spark to run on Spark, Yarn, Mesos, and built-in software. Tomorrow, if there is some other resource manager, all you need to do is, all Spark guys would do is, they will just implement a new cluster manager, and the rest, the Spark will be able to run on it. All right. Next is, so when we ask driver to do something, driver asks the cluster manager or resource manager, and resource manager goes and talks to the individual machines and get your work launched on various machines. There could be multiple executors. There could be multiple executors on multiple machines. And this is what goes on. So whenever we say, when we say map and then action, this is what is going to happen. Until we say action, it's not going to talk to resource manager. It's going to just make a note of what all you are talking about. So the moment we call an action, it's going to talk to resource manager, then execute your logic. Like here, there will be one partition being processed, here another partition, here another partition being processed using either map, flat map, or any other method that we've used. And there, this is where whatever code you're writing, like the way we wrote how to compute the hash code and other things, all of that code will be run inside executor. All right. So the executors, the worker, these are the worker processes that run tasks of a job. It returns results to the driver and launched once at the beginning of Spark application. So the moment you say action, it launches the Spark job and it launches the executors. It runs for the entire lifetime of the application, and then it provides in-memory storage for cached RDD via block manager. So every executor's duty is to maintain the cache, right? Whenever we are saying persist or we are calling cache, it is going to keep the data in the memory using something called block manager. All right. So whenever we are executing the task, driver is going to talk to resource manager, and these are the tasks that are being executed on the executor. There could be thousands of machines, and these tasks could be parallelly processing your task. You could be running map, you could be running reduce, you could be running flat map. Inside that, your code will be sent to all the machine where the code is going to run on the data. So the task kind of takes the duty of maintaining the cache of the RDD and executes the workload. All right. And the driver converts the user program into tasks and launches Spark applications. So this is what goes on. When the Spark submit happens, it goes to the driver. When the user submits the Spark application, user is talking to the driver, and driver is talking to the cluster manager. It could be Yarn, it could be the local one, it could be standalone Spark, and so on. And then the Spark, then the executions of the various tasks are started. And then when the program exits or stops, then basically everything shuts down. Okay. Now there are two modes called local mode and cluster mode. When we do not pass anything, the program is running in local mode. And this is specified by an argument called master. So right now, question is driver a name node here? Not really. We'll learn that part soon. So there are basically two mode. One is called local, other is cluster. Further, cluster mode has multiple modes. We are going to talk about it soon. Now, the local mode or Spark in process mode is the default mode. It does not require any Hadoop or Yarn or any other thing. It can run on your desktop, on your laptop, or anywhere, right? So it's basically a pseudo mode. It does not require any resource manager. You can simply download and run. It's good for utilizing multiple core of your machine. If you just want to process your data using multiple cores of your machine, you can use this mode. Even if you don't have like whole cluster, still it'll be useful for utilizing the cores. Partitions are generally equal to the number of CPUs. This is generally used for testing or for the development. All right. So the default partitions when you create in this are generally a function of how many CPU cores do you have. That's why when you say sc.parallelize, it'll create like four cores, four partitions by default, because we have the 4 cores on the machine. All right. So by default, RDD, if you are running in this mode, by default, the RDDs will have partitions equal to the number of CPUs. Okay. So we can run Spark Shell Spark submit with Spark shell, or Spark shell dash dash master and local, and then you can pass the argument a number in square brackets. Okay, we're going to talk about it soon. So what's happening in the local mode is here it's the same machine on which the Spark application is going to run, and the driver application is here on the same machine. All right. So to check which mode you are in, you can always use sc dot is local. Let's just check sc dot is local. So it is true. That means we are running in the local mode, right? And to know who is the master, as in the information about your cluster, it says it's a local machine with asterisk. What does it asterisk mean? Asterisk means the number of threads. So this asterisk here means the number of threads that you want. You must use minimum of 2 threads. So you can actually say master. So Spark shell, if you don't pass anything, it is going to use only the local one. Local, it's going to only use the local machine. It's going to run in the local mode. So if you want to say specify that I'm only looking to dedicate three threads to this particular Spark driver. So we can say this. Okay, so it's going to only you keep 3 threads and not 4. Okay, so we can control that, but that's not a wise idea. You should generally just, if you're running in local mode, don't specify anything. Or if it is mandatory to specify master, then you specify asterisk here. That means as many threads possible, run those many threads. Okay, so that's what it means by the local start. So asterisk here represents the number of threads that you want to dedicate to Spark. Yes, you have something to say?
Yeah, I have a question over here.
Okay.
I was just wondering, like, how does it happen in the commercial space? Like, does the program run infinitely? Like, how would the architecture work in when it's working at a commercial space?
At a commercial space, the general idea is that okay, so by default, wherever you are developing or doing testing, people generally run in the local mode. All right.
Okay.
And usually when you want to push it to production, you use the master argument, or you launch it using Spark submit and pass the same argument as this Spark dash submit and then dash dash master, followed by local or say yarn, or we'll talk about those. All right.
But when you do Spark underscore submit, and
Right.
if you have like different classes interacting with each other, will that also be taken care of?
Yeah. So you
Like,
basically passed all of the code in the argument and it will take care of everything.
okay, so that Spark underscore submit will take care of everything.
Spark dash submit will take care of everything.
Care of everything. Okay.
It'll take all your classes, install on all machines, and will run it there. So you don't have to worry about class clashes or carrying the classes to all the cluster and so on.
Yeah, that is what I was wondering. Like, how would it happen in the commercial space?
Right. So you have many arguments on Spark. We're going to talk about those very soon. All right. A question from Sachin is a default number of threads, like how many threads to dedicate to the driver or Spark. Generally, you must give more than 2 threads if it is really you want to control it. But generally, people don't really want to control number of threads. They put asterisk. All right, whatever threads are available. So because every program needs number of threads to process. So if you are giving less than 1 thread, then the Spark won't work very well. Okay. Now, the second mode was cluster mode. First one was local mode, other was cluster mode. It can run on the cluster either standalone, on Yarn, on Mesos, on EC2. All right. So the standalone is when in an organization you don't have cluster, but you have machines. Okay, let's say you have hardware, but you have not set up a Hadoop cluster yet. Okay, so in that case, what you can do is install Spark, as in copy the Spark on all the machine, inform all the nodes about each other by updating a particular file, and then launch Spark on all the nodes. The Spark will automatically discover each other and will automatically form the cluster. Okay, so this is called standalone mode. This is rarely used. Mostly people use either with their own cluster of Hadoop or with their Amazon instances. All right. So essentially, this is what it is. If those of you who are interested, we can discuss it offline, and we can try it offline. So all we need to do is copy a compiled version to the same location on all of the machines, set up a passwordless SSH access from your machine, your master machine to another, edit the conf slaves file on your master and fill the worker's host name. Then we run start all that .sh on the master, and then we check the master's this particular node, and that would show you that the master is running well. So again, it's a master slave kind of architecture. Basically in the master we update all the slaves, and on all the make the slaves controllable from master by setting up passwordless SSH. All right. Now the second cluster mode is yarn. To run Spark inside Hadoop's yarn, we need to specify these two variables. These two variables are very important variable for Spark. This is how Spark discovers Hadoop. How? It basically, when we run Spark shell, it's going to look for these two environment variables, and when it discovers either of them, then it goes into the configuration folder, picks up the configuration file, and then looks into Hadoop's configuration, who is the name node, who is the task tracker, and so on. Okay, based on this folder, it figures out everything about your Hadoop installation. All right, so the way you run the Spark in the yarn mode is very simple. What you can do is you can simply call it like this. You could say Spark shell dash master, and then you can say yarn. Okay, it's going to talk to yarn. Okay, keep this in mind that we need to all right, keep this in mind that we're going to talk to uh, Spark yarn, and it might take a bit of time to set up everything in the yarn. All right, so here, since I'm in the yarn mode, now I can do, let's say, where rdd equals sc.txt file. Okay, I'm just going to show you. Let me just load it from. Oh, I have not. Did I export those variables? No. Let me just export the variables and launch it again. Okay, so you can also try if you want. So this is how you interact with the yarn. You can see it's trying to talk to yarn and trying to register itself with the yarn. It might take a bit of time in the beginning. It's trying to establish a long running process with yarn. All right, looks like we are done. Now let's say where rdd equals sc.txt file. I'm going to use the same one and say data.mr/mr/word count/input. Okay, so this is what we are going to do. And we are going to say rdd.tick 10. All right, just to check if anything is working. So it has basically brought the data. Now let's take a look at what was the port on which it got started. Okay, so this time, what, 4041. Okay, 4041. All right. One more thing you will notice now is the logs of Spark will come through yarn. If you go to Hue and click on job, right, you will see this job that is running still. Okay, this is the job of Spark, which is still running, and it's a long running job that has been dedicated to Spark. Okay, you can't see the logs yet. Okay, so the important part is when you are running, say, Spark Shell or Spark Summit, the job is going to appear part of yarn. These are the jobs of yarn. Because why did it happen so? Because we ran it in the yarn mode. All right, because we ran it in the yarn mode. All right, so in the same way, you could try doing the bigger processing, and you will notice that it is distributing the work in the cluster. Okay, right now it's not able to give us this, but if we exit it, then we'll be able to see we'll be able to, let's also take a look at e.cloudxlab and say 4041. Okay. Oh, it's redirecting us to, oh, it's redirecting us to A. And all right. I see. I see. Okay. Never mind. So we'll have to probably take a look at this one separately if we can avoid it. All right. So great. Basically, the log UI is not being accessible from outside. Okay, great. Now moving ahead. So what we just did was we were able to successfully run our job in Spark. Because why it's happening so? Because the log has been moved, the job monitoring has been moved to here. Okay. A question from Sachin is, can you explain what yarn does? Remember, yarn is essentially a way of job execution on Hadoop, right? If you have a Hadoop cluster and you have 50 machines, if you want something to be done on those 50 machines, you will have to utilize yarn, all right? And that's what Spark is doing. So Spark is talking to yarn. Instead of reinstalling our cluster, new cluster just for Spark, we are utilizing our Hadoop's cluster, and that would be the case in most of the industrial applications. All right. So all you need to do is you have to export these two variables, and in case you want to take a look at how do we submit our Spark application, we'll generally say Spark submit and master yarn, and this is the class and so on. All right. So this is the way we can run our application in the cluster. Those who want to give it a try, they can give it a try and take a look. This is essentially the jar file. The way we can, in the same way, we can create our own Spark application and run it via Spark Submit. Okay. So here we are saying Spark Submit. Okay. So yes, there are a couple of questions. Let me answer those. So first question is from Bintao. What is the detail constructor syntax of Spark Submit? So here you can see, here we are saying Spark Submit master yarn. Then we are saying what is our entry point. right? This is the class which is the object in this one so that it can be run. And then we are saying that this is the jar file. What is jar file? Jar file is like zip file. So it's like a zip file that we are handing over, or the list of zip files we are handing over. And then we are passing whatever argument is expected in the main method of this class. All right. So let's just, you can try running it. We had already run it once. Okay. So this is how we could interact with Spark on Yarn. All right. So all right. Similar to Yarn, we have something called mesos. If you're interested in mesos, we can have a separate discussion. But in simple words, we can also run on mesos by simple method like spark submit dash dash mesos and then providing the URL of the mesos. Rest of your application will remain same. So whatever program, whatever things we learned about RDD and key value RDD and partitions and so on, all of that remains same. All we need to do is just change the master URL. That's all. Okay. All we need to do is change the master URL. A question from Hitendra is Spark Submit did not work. Why do you say so? Do you want me to take a look at it? Yeah, go ahead. Okay. All right. So, okay.
Sandeep, is Spark
No, no,
submit will
this
submit the job.
you have to run on the shell. All right, Hitendra, you have to exit. Yeah, thank you, David. Okay. Yeah, Sachin, you had a question.
Yes, Spark submit will submit the job or submit our code what we have had written.
Come again, please. I was a
For
copy.
example, we have run some Spark code.
Okay.
So Spark submit we can submit it.
Yeah, yeah. So all you need to do is compile the code,
Yeah.
right? So okay, you want to compile the code? All right, I'll just show you. All right, some of you wanted to. Okay, so let's take a look at a simple project. Those who have not done it yet, we can do it now. Okay, so all right, let me just show you how to create a simple project. All right, let me just show you that. Okay, so those of you have not checked out this repository, you can check out this repository. Okay, so you can say git clone and this in your home drive. Okay, so once you do git clone, okay, git clone, right? This repository will come to you. Okay, for me it's already there. So all I need to do is go into that folder and refresh it. We say git pull. Okay. So when you do that, this whole code that you see at GitHub will come to your home drive. All right. So when you say here, let's take a look at, say, Spark project. Here, the right. Let's take a look at this project. Okay. This project is having this source file. Okay. You can actually create your parallel one. Don't need to worry about doing that. You can just simply edit your code here. And let me just see if I could demonstrate something. All right, so this is the one that would show you the entire project. So generally, when you are building a proper project in Spark, what you need to do is, first of all, you need to define build.sbt. Okay, build.sbt. Here in the build.sbt, we have told that our program depends on Spark core. Since we want our program to be backward compatible, so we are going ahead with really low version of Spark. Also, since we want to do testing, we are depending on this project. Here, this is the name of our project. Here, this is the version, and this is the Scala version, minimum version of Scala on which we depend upon. All right. So if let's say you're creating your own project, so you can you can actually create the project using Jupyter. You could go to CloudxLab, MyLab, and then create using Jupyter the same way, right? You could just create a folder just like this, create a file like this, and copy paste these things. Okay. So I think a better thing would be that you do it at your own, because this is very much required. So your build.sbt should be looking like that. Okay. Now this is not much required. Okay. Then we are saying this is readme file in this folder. So this is the only one that's required. Then we must have src folder. Inside src folder, you should have this kind of a folder structure. So these are very empty folder structure. So test, there are two folders, main and test. Inside main, there is another folder called Scala, com, CloudxLab, log parsing. The one, all the folder structure inside main is for main programs and test for testing. Okay. So inside main, you have many languages. You could have Java, Scala, and others. And then is the package name. Okay. Package name is optional, but it is always suggested to have the package name. And then you can define your classes, right? So you must define a class like this as an entry point, and then basically in that you can have your arguments and so on. Okay, arguments and so on. So let me just show you running this project. So in this, it's basically a very simple program. All it does is it has the main method with these arguments, and it basically creates the Spark context. Please notice here that we are creating the Spark conf object first. Then we are creating a Spark context object. These SC, this SC is the one that was available to us all the time. We were calling SC dot parallelize, SC dot this, and so on. But here, this is something that you need to create. All right. And then you have to set the log label. You must try to mm, write your program this way. So all you need to do is create a fresh folder, create a build.sbt like this, then create src in that. Inside src, you create main. Inside that, you create Scala, and then the full namespace. This is up to you what you want to keep the name. com.cloudxlab.logparsing. You could say Hitendra, like com.hitendra, or any name that you want. This is just to separate out the namespace. Okay. And this is how the main method looks like. All right. This is how main method. This is the most important part. Okay. So this class must have, this file must have this kind of thing: object, entry point, and then define main, and this. Okay. In this, the first few lines will go into creating the entry point, and then remaining would be your usual program, the one that you were doing on the console. All right. And remember to import these values. All right. So let's take a look. So since we have pulled the fresh data, now we could go cd /spark cd projects. Okay. And then we say Apache underscore SBT. So you can see this is the folder structure. All right. Now let me just delete the target folder. Okay. So the way generally you compile the projects is using the build tool. Here we are using SBT. SBT is the one that is generally used. So we are saying SBT clean. Okay. Clean removes everything that was built previously. Okay. So now this target folder would be probably empty. Yeah. All of this is empty. Project folder, let's just check what is right. So you can just delete project folders as well as the target folders. All right, so now it's kind of empty. So we can say git, not git, we could say SBT and we could say test. Okay, it's going to run the test cases. Or we could say sbt.jar. It's going to run the jar, create the jar. Sorry, not jar, it is supposed to be package. I always keep confusing with other one. All right, so it has done the packaging, and packaging, after packaging, it has put in this folder. Okay, now we can do spark dash submit. So it says that you did not provide these arguments. Okay, you did not provide these arguments. So we could just specify whatever argument it is asking for. Oh, there is a bug in this. Okay. All right, so it is able to give us these top 10 arguments. All right, so basically we were able to run this piece of code. Okay, so this is the point that was printed. This is multi-line string by triple quotes. Okay, so when we noticed that the argument list was not equal to 3, then we basically printed this usage. Okay, that's what was happening, and once that was working, then we called this. Okay, so all we did was, sure, I'll give you the code. So this was the last command. Before that, we did SBT package. Okay, then.
So Sandeep, if we have a dot class, only one class file, then also we can submit like this, or we need to convert it to jar?
So you can actually submit the individual. No, you will have to compile it. You will have to compile it. Although Spark Submit takes the script as well, but I would suggest that you compile it. So
we have to put into form of jar.
yes.
Either it is a single class or multiple class. Nothing.
I mean, the Spark Submit allows you to even submit a Scala script or but generally in the production one, you would like to create a jar. Okay.
Jar, var, or ER also.
I'm not sure. I think basically anything that is in the form of jar, it would take. Okay.
Okay.
So ER also is kind of derived from the jar only. So most likely it should work, but I'm not really sure. Okay. So yes. So what all did we do? Okay. So all right. So what all did we do? We exported these two lines, right? Okay, then we did this. All right. And after that, we did git clone, right? Correct. And then we went into big data. Then we went into projects. And then we went into this folder. Yes, let's take a break. All right. So, and this here we did. So you could try the same thing. All right. So let's take a break. All right. So let's get started. So before the break, we tried to create our own jar and try to run it using a Spark Summit, and we were able to successfully run it. Instead of creating from the scratch, we used the Apache log parsing SPD project. Okay, so all right. So here, basically, we are saying Spark Summit. We are passing master yarn. We are telling the Spark Summit to run on top of yarn, and then we are telling that this is the name of the class, and this is the folder that contains the next argument is the folder that the zip file or the jar file which is there. Okay, and then 10. All right. So since our project only had one folder, right? So
What is the Spark Pi?
what?
Spark Pi.
This was an example. It's a class provided. It's a name of the class which is there in this folder. All right.
Okay, we have to mention the class name.
Not always, not always. In our case, we did not have to do it because there was only one class file.
Yes. So this is our custom class, example.sparkpy.
It's not our custom class. It is the class. In this example, we are showing that there is a folder called Spark examples, which are provided ready-made. Okay. And in that jar file, there is a class with this name,
Okay, that
org
is
slash.
user defined class.
Yeah,
Okay.
which is provided as examples to Spark. All right. Okay. Question is, what is the expected result of this? The expected result of this is you will see the value of pi being listed. It's a program provided by Spark out of the box, which computes the value of pi using Spark. All right. In our case, we have tried to find out top 10 IP addresses from the files. Okay, which is part of the project, which is just one part of the project that we have done as part of the the GitHub repository. Okay, so we could also put our code here. We could just duplicate this slide and put our code here. All right. Okay. Let me just remove the bullet points. That's pretty much. Okay. So all right. So this, you can see that this is the code, and this is a single command that we have here. All right. Great. All right. So what we did was we were able to run our own project as well by this mechanism. We were able to do Spark submit. We could have done the Spark submit and we could have said master yarn here. We could have said the same thing here. In here, we could have said the Spark submit. If you want to run in the yarn mode, we could say master yarn. Okay, so it has executed the job. You could take a look at d.cloudxlab, and as part of job browser, you will be able to see that the job called the job name is still word count. Okay, why? Because probably that's what we have mentioned in the file somewhere, probably here, while defining the name. Okay, why does it show word count? Did we say something here? Spark submit. Okay. Maybe in the program somewhere here. Here. So this is where we have specified the app name called word count. That's why you see word count here being shown. Okay, so it has successfully run it. And if you see this kind of error, most likely you will have to go to the local IP address with respect to this. What is the local IP, public IP address? You can go to the MyLab and take from the IP mapping. What is the name of this one? This is 153.153 b.cloudxlab. All right. So you could do that because the machines know each other from their local IP address. In say an organization, you will be allowed to access the local IP address. That's why you will not face this kind of problem. In our case, since ours is a public cluster, we don't want to expose our internal addresses to the public. Therefore, there is a difference. All right, so you can see that the job has successfully run on Spark. All right, so this is the important part. And okay, so let me just put that second command also here. Okay, so this is a multi-command, okay, multi-line command. So we have to be careful while copy pasting. Great. All right, so now in the same way, you could also run it on Amazon EC2. It provides it provides a command called spark-ec2 that launches the Spark EC2 script. So all you need to do is use this command to submit your jobs. All right, spark-ec2. Now that we will take it offline, probably the demonstration of Amazon EC2. Okay, that's actually pretty straightforward. More important is to understand that we can actually run our program on top of EC2. A question from Sachin is, can you explain the output? The output is basically top 10 IP addresses. Please go through the code, then you'll get the idea. All right. So which output you're talking about? You mean this one? The output that you see?
Yes, yes, yes.
It just go through the code because this is basically we are printing the output of take. All right.
Okay.
Okay. Yeah. All right. So the more important part here was that how to run our program. We have talked about our key value pair RDD and all of that. And that program does all those things. Now, again, further to the cluster mode, we can run in two basic ways. So there is something called deployment mode. Earlier we talked about the master, or you can say cluster mode. Now the second part to execution is the deployment mode. Deployment mode is based on where does the driver run. Does the driver run on the same machine on which the user is logged in, or does the driver run somewhere else? So there are two ways in where there are two places the driver could run. The driver could either run where the client is, or the driver could run inside the cluster. Okay, so the client mode launches the driver program locally. This is the default behavior. The second one is the cluster mode, in which the driver is running on one of the worker machines inside the cluster, right? So here, let's say you you are basically, this is the driver application, this is where user is. So driver application interacts with resource manager to get the work done. So driver application, if you are running in something called yarn client mode, okay, this is the deployment mode is client mode, then even though you are running on yarn, the driver would run on the same machine on which the user has launched it, or some script has launched it. So driver application, if the driver application somehow shuts down, the process will be killed and nothing will proceed. So it does not provide a resilience. Mm, okay, so like the right now we are running Spark shell, right? If this program is killed, then nothing will happen. It'll stop and no processing will happen. But the other mode in which you run in the cluster mode, the driver application runs inside the yarn in application master. If launcher shuts down, let's say this user has given the Spark submit with the yarn cluster mode, then your driver would be running inside one of the applications or inside one of the nodes. If the launcher shuts down, as in this user disconnects, then the process continues like a batch process in the background. The preferred way to run the long running process. This is the preferred way to run the long running process. Okay. So we can, right. So we could export these two environment variables, and then we can run in the deployment mode called cluster. Okay, if you want to run a program in the cluster, we could call it like this, and rest of the things remain same. So just by default, it runs in the client mode. If you want to run inside cluster, you just need to specify this particular line. Okay, to if you want to check the status, you will be able to check using this and so on. So basically, when you want to run even the driver inside the cluster, you could use deployment mode cluster. All right, so let me give you a demo. All right. Okay. Basically communicating internally, and once everything is finished, it'll be shut down. Okay. Now, where is my output? The output you won't see here, the pi value and all those things, because it is now inside the yarn. Okay. So here it was succeeded, and inside it you can go to logs. Logs again, we'll have to find out where is this IP address. This is 153, correct? 153 b.cloudxlab. Okay, so why did it not found? Is this not the one? b.cloudxlab.com. Yeah. Actually, I made a typing mistake. So you can see that it ran, and this is where it got executed. And you can see that the Spark tree is there. With the Spark tree, it has all the details about the process. Okay, and all right. So this is where it ran. You can see there were two IP addresses. Now, who was the driver? 179. Who is the 179? Oh, the driver was still e.cloudxlab. Okay, and this one was 153. 153 is B. Okay, and 179. Sorry, yeah, 179 is E. So basically, it executed one part at one machine and this part on another machine. And if you want to take a look at the std out, you could click on std out. And again, 153 need to be updated. All right. So this is where your output is. Okay, you could click on the full and there you should be able to see the result. Okay, now going back. All right. Now let's take a look at this std out and this std out. Okay, again, b.cloudxlab will have to replace. Okay, so it should have displayed oh, I think the driver, we need to take a look at the driver's std out. Driver's std out will be on this machine, which is this 179 is what? 179 is what? E. E.cloudxlab. All right. So this is the driver's output, and you can see here it says pi is roughly 3.1392. Okay. So you can see that when we are executing the driver in the cloud or in the cluster, it saves the logs on the cluster. All right. Instead of running driver locally, driver is executed by yarn. All right. That's the important bit. And if the driver is running on yarn, the result will not come on the std out will not come to standard output will not come to your console. Instead, it will be in the yarn's logs, Hadoop's logs. Okay, you'll have to go to that the logs and then take a look from there. Okay, if you get IP not found, replace the private IP with the public IP, and that's the way you can debug your process. All right, so that was how we run something in the cluster. A question from Sachin. So every code we submit there is a corresponding job for it. If it is running inside Yarn, there will be a corresponding job for it. Okay. And question from Minta is, where is this? You can go to the std out in your jobs, then it'll run. Okay. So let me also give you the code that I ran. A question from Grisma is, I cannot access the lab. Okay, so what error do you face while accessing the lab?
Hello, Sandeep. Earlier I used to get login incorrect, but now maybe because I tried multiple times to connect, now it says deactivated.
Oh, is it?
Yes.
So in the console, it's giving the error?
Yes, I mean, if I try to connect to the log, right, web console and Jupyter.
Yeah, can you just drop an email that reaches that you're
Okay.
not able to access?
Okay,
Okay,
sure.
all right, thank you. Now, going ahead. So this was quick overview of how to run Spark in various modes. Question is which cluster manager to use, whether to use Yarn, local, or standalone. So start with local mode if this is your new development. To use richer resource capabilities, example queues, use Yarn or Mesos. When sharing amongst many users is the primary criteria, then you should use Mesos. In all cases, it's best to run Spark on the same node as HDFS for fast access of the data and the storage. You can either install Mesos or standalone clusters on data node or Hadoop distributions. All right. On Hadoop distributions, all Hadoop distributions already install Yarn and HDFS together. All right. Next is you bundled all the libraries the program depends upon. No need to bundle the Spark libraries and language libraries with it. Python users can either install the same program using pip or easy install on all the machine. Okay. And for Java and Scala, submit libraries using jars, but there are many libraries use build tools such as SPT or Maven. All right. Sachin's question is, can you give real-time examples in which we can understand the Spark submit code? What do you mean by Spark submit code? Do you mean the one that we are using, Apache, the one? So
I mean, like any real-time example of where we can use Spark. Because, for example, consider a e-commerce company. I think they have generating a lot of data, so they are using Spark.
right, right. So wherever you are processing the data, use Spark, and yeah, every company wherever you are executing programs processing humongous data, you'll be using Spark or Hadoop or some system or like that. All right. So as we discussed earlier, or we can have a separate discussion, or you can leave the question on the discussion forum, because we have discussed this part, and because all of this, whatever we have talked about, is a real-time use case, and I would love to answer this in detail. All right. So is anybody having the same question else? I would love to answer it now. All right. So I think Sachin, we could discuss it offline. And yeah.
Okay.
Yeah. Okay. So all right. So basically, you can bundle everything using SBT, and that way you can basically take it together. Also, if you have external jars, on this Spark Summit, you could pass dash dash jars, and you could put more jar files there. And if there are too many libraries, you could use SBT or Maven. Now, master this one, which we have discussed. A question from David is the command line. Oh, okay. So I think the question was to Sachin, right? Or to me? All right. Okay. So Spark Summit, the flag dash dash master that we passed indicated which cluster manager we are connecting to. Dash dash deployment mode told where to run the driver inside the cluster or outside the cluster. And the name we could also, in Spark Summit, we could specify the name of the application. All right. If your application is not overriding the name, then this name will be used, which will be reflecting in our Yarn as well as the Spark's web UI. If you have a list of jars, you could say dash dash jars and put all those in comma separated way. And those jars will be picked up for if your program depends upon it. Let's say you are writing an emailer, which is going to send 1,000,000 emails. Then you could say, you could use dash dash jar flag and run it using that. Okay, you could say dash dash jars, and essentially whatever, say Java mail you're depending upon, you could use Java mail in the argument. Similarly, if there are many files that you want to be copied in the target, then you will use dash dash files. And in case you have Python programs on which your program is depending, then you will say spark submit dash dash py files and then specify that file. Similarly, if you want more executive memory, then you could say dash dash executor memory, as in what is executor memory? The memory that is used while your program is executing on any of the nodes in the cluster. So this is the amount of memory to be used for the executors in bytes. Suffixes can be used to specify larger quantities, say for example 512 MB or 15 gigabyte. Similarly, if your driver requires bigger memory than the default, you could use spark submit dash dash driver memory and specify how much memory you would like to use. All right, so that was pretty much about running on the cluster. All right, now let's go over the advanced programming. So most of these are basically the flags you could use to optimize your Spark program. All right, so in continuation with the functionalities provided by Spark, when we pass functions such as map, every node gets a copy of the variable. The change of these variables is not communicated back, right? Whenever you make a change. All right, most of the slides are okay. All right, let's go ahead. So here we are back to the advanced programming. So after running on the cluster, now when we pass functions such as map or anything, every node gets a copy of everything, right? So let's say you have a map function. Your function is referring to some other local variables and so on. So whenever we are passing functions to map or any other flat map or any other function, so your code is going to be distributed on all the machines. That's right. So, and along with the code, it will also refer to all the variables that it is depending upon, and therefore one copy of each of those variables will go to all the machines, right? So as we discussed earlier, that when we are launching something on the cluster using Spark, it is going to send your code to the executor inside a Spark application, which will be run on every machine, right? So there, that means that whatever code you write is going to be compiled and is going to be sent to all the machines, right? And when we pass functions to map or anything, that code is also going to be executed on all the machines. And if that code is depending upon external variables, those variables copy will go there on all machines. But the value will not be communicated back. If the map function changed a particular variable, it won't be communicated back, right? So, all right, it doesn't impact the worker. So there are better ways of sending the data to the cluster and receiving the data from the cluster instead of normal way. The first one is accumulator. Accumulators are basically for receiving data from the cluster. Okay, so let's say you want to monitor the progress of your application. In that case, you can use accumulator. In accumulator, all of your Spark applications running on all machines, they will keep on giving you the data back here. Let's say this is printing the logs or giving the progress. They can basically give you the real-time feedback, the real-time logs of the process. All right, for those you can use accumulator. You can create your accumulator variables and keep on appending to those variables. And when you are appending, as in your program is appending here, 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 and here, those variables will be received here. So basically, accumulators are variables that are only added to though through an associative operation, because these are sequential operations. So there's no guarantee that whatever you're doing will happen from before another operation. So these are only append only operations. Okay, you cannot update anything. So because this is happening in parallel. All right. So let's say you want to count how many empty lines are there. So what you will do is you will first create the folder. You first of all create the RDD from the folder, and then you'll create an accumulator called number of blank lines. Then you have defined a function called, say, two words, and in the two words, what you're doing is if the line's length is 0, then you increase the number of blank lines. Otherwise, you call this a split function. Now, when you are increasing this, it is essentially calling your accumulator. You're appending to the accumulator. And then you can say flat map and save to text file. So whenever this would happen, this is an action, and this will call the flat map. Flat map will basically execute this function on every record. And when this function gets executed on every record, here every record means the line, single line, because we are using sc.text file. That's why the RDD that is created is RDD of lines, a kind of array of lines. So the two words, whenever it encounters the line is blank, it is increasing the accumulator, right? So this way, yeah. So here, sc.accumulator, we are saying that this is an integer kind of accumulator, and the initial value is going to be 0. All right. So the number of blank lines is not really an integer, but an instance of accumulator containing integer. It's like a big box. It's like a box which can store the values of type integer, where initial value is 0. So here, specifying 0 does two things. One, it figures out that we are trying to create accumulator which will store a number. While specifying this also initializes it to the initial value of 0. All right. So you could try this out. You could try this out. All right. Sorry, Spark shell. Okay. So here it's saying the file already exists. So we'll give it some other name. Let's call it 28th April. Okay. So all right. So it has finished it. Now let's check the environment variable, this number of blank lines. So you can see there are number of blank lines are 24,858. All right. So this way we could interact with Spark and use the accumulator. All right. So this is called accumulator. Accumulator is basically for accumulating the variables from all the nodes. Now, quick question to all of you, that we have heard that if we are running on Spark and some job fails, then it's going to re-execute the failed or slow tasks, right? So So will this execute one function multiple times? So let me go back here. Since we have heard that Spark might relaunch something if something fails, so can the two words function be executed multiple number of times, more number of times than required? Quickly. Let's say one of the partitions fail and Spark launches the same program somewhere else, right? Will these two words start from the beginning or will it resume from where it left? So these two words will be executed on all the machines in the cluster where the RDD is located. So it might be executing on multiple machines simultaneously. So if one of the machines fail, then the same work will be executed somewhere else. And hence, these two words could be executed multiple number of times. All right. So same function may run multiple number of times on the same data. So accumulators and fault tolerance basically does not go great together. So if you have fault tolerance in place, the chances of accumulators giving wrong results is very high. All right. So yes, accumulators in transformation give wrong results while accumulator in action give right results, because if action is not completed, then accumulators are not really counted, while the accumulators in transformation give the wrong results. All right. So if you are using accumulators in action, each task accumulator update is applied once. So let's say what does it mean is the way we are increasing number of lines here, if we were doing it inside reduce function, it could have been okay. But inside two words, because it's going to be called via flat map, and hence it's going to be a part of transformation. Therefore, this particular line might be executed multiple times on the same data in case any of the nodes fail, right? So be careful while using the accumulator. Do not consider the accumulator like truth, like a transactional data. Consider the accumulation as more like something that you need urgently, but you're okay with minor number of mistakes. All right. So, and if it is important for you to have like exact values as a result of accumulator, then use that only in action. Don't use it in the transformations. All right. So out of the box, Spark supports accumulator of type double, long, and float. Spark also includes an API to define custom accumulators. So you can define your own custom accumulators and you can define it in this way. All right. So you can take a look at this particular code if you want to really define a custom accumulator, although it's not really required to define the custom accumulator. All right. If you are looking for defining a custom accumulator, in case of version 1, it was like this. In case of version 2, it is like this. All right. So you could define your own custom accumulator in this way. Now, the other kind of variable is called broadcast variable. So sometimes, let's say you want to send one particular in-memory variable to all the nodes. You have a local variable. There are multiple ways, right? One, you could do sc.parallelize. Other, you could just refer that variable from your method. So either of the two things you could do, right? But both of the things have their downside. So if let's say you want to share a particular variable with all of the machines, so one way could be we could say sc.parallelize and convert this common words into an RDD, right? So and then you join it with the actual. That's the right way to do. But if the data is something that you really can't join, instead you want it on all the machines, then if you just refer this from your function, then also you will get that variable on all the machines. Okay, but that's not very efficient. That's not very efficient, and that's where the broadcast variables come into play. Let's say um, you want a particular piece of data on all the machines, and you want it locally, then you should use the broadcast variables. So let's say if we need to remove common words from our word count, what do we need to do? These are the common words, for example, and these common words could be in the file. These words could be in the larger content. So what do we need to do in order to remove common words from our word count? We can create a local variable and use it, right? Then also it's fine, just that it is a bit inefficient because Spark sends the reference variables to all the workers, irrespective of whether it's required or not. The default task launching mechanism is not optimized for small task sizes. So if you are using multiple times a particular big variable, then Spark will be sending it again and again to all the nodes. So instead of just referring a variable from your code, like common words or something, instead of that, you use the broadcast variable. All right. So broadcast variables are sent to all the Spark application. All right. A question from Rajan. Basically, we can avoid having to do reduce function by using accumulators. All right. So good question. So basically, we can avoid having to do reduce function by using accumulator. So yep. So it looks like that we can avoid, say, counting and things like that. But the accumulators are only one way and are not essentially very safe when it comes to accumulating values because they can be executed multiple times. They can be executed multiple times. All right. So yes, most of the counting operations can happen, but in the reduce function, we could do max and min, but that you cannot do in the accumulator. That you cannot do in the accumulator. Accumulators are only append-only variables. A question from David: why are there both single quote on 25? Good point. This one, yeah, we should have actually used the double quote like this. Actually, this is supposed to be a list. Just for simplicity, we have given it like this. So if we have something like this, okay, I think that now this is okay. Now the simple answer is that we are quite used to Python, and that's where the single quote comes from. All right. So broadcast variables are used to efficiently send a large read-only value to all the workers. For example, we want to send the lookup table to all the nodes. Large feature vector, let's say you trained a machine learning algorithm and you want to say send the machine learning model, or maybe a large feature vector that you would like to send it to all the machines, then that you can there you can use broadcast variable. So it is like the distributed cache in Hadoop, and Spark distributes broadcast variables efficiently to reduce communication cost. All right. So it's useful when tasks across multiple stages need the same data. Caching the data in deserialized format is important. So, so when you need the data to be on all the machines, then you generally prefer to use the broadcast variables. Now, let's take a look at how to use broadcast variables. Imagine that we have the variable containing all the prepositions and very common words, and then we are defining a hash map. We are defining a hash map containing the word and one. All right. Then we are creating a broadcast variable around this hash map. Okay. And then we are doing the word count. So inside the two words, what we are doing is we are checking if the word is common or not. Okay. If this common words dot value contains this particular word, then it does not contain, then we are appending the word. Otherwise, we are skipping it. So here, what we are doing is we are going over whole line, iterating over the words, and iterating over the words. In case the word is existing in our hash map that we created above, then we are not appending it to the output. All right, and then using the flat map to call our two words function. So this is how. The important part to notice is that common words BC we initialized with our data, and then the way we are using is by the way of common words BC dot value. This is what will give you the access to the hash map. Okay, and then we are checking contains this particular word or not. So this way we are able to utilize the broadcast variable to send the common variables to the whole cluster. And in case we are doing the word count on not so common words, then we could use this. All right. So all right. So this uncommon words, we can just take a look at uncommon words. Sorry. Let me just give you the whole code. So I've copy pasted the code, or you could take a look at this particular. All right. So this way you can access the common words. All right. So what we learned was that if we say take 20, then it will show only the not so common words, though by is there. And did we remove by? No, we did not remove by. So this way we'll keep on adding more and more common words, and we can remove those common words from the book. All right. All right. So let's yeah, that's how we run the that's how we utilize the broadcast variable. So in case you want to gather data from the cluster on continuously, then you use accumulator. In case you want to send the data to the cluster to all the machine where the data would be required, you would use the broadcast variable. Now, all right. The next thing is we could improve the performance. We could improve the performance of our Spark application further by in this way. So far we have learned about partitioning, we have learned about sorting, and the we have learned about how do we run something on the cluster, and we have also learned about broadcast and accumulator variables. So the further, if you want to improve our Spark applications performance, we could do the following. The first and foremost is level of parallelism, meaning how many by default, how, so meaning how many tasks do we want to execute in parallel. So by default, there would be one single task per partition. Okay, so if you have 20 tasks, if you have 20 partitions in your RDD, if you have 20 partitions in your RDD, there will be 20 parallel tasks. A single core in the cluster will be dedicated for one task to execute. Hence, the more partitions you have, the chances of it being more parallel is high. So Spark provides you one key thing to control parallelization. Okay, Spark provides you one thing to 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 control the parallelization, that is number of partitions. All right, because there is one task per partition and one core in the cluster to execute. So default partitions are based on underlying storage or the CPUs. Or it could be our choice as well. If you are loading the data from HDFS RDD, there'll be one partition per block. Okay, a question from Binta is, could you explain the syntax where common words map equals collection.mutable.map? So we are basically creating an empty map of collection. Sorry, we are creating an empty map from collections, and this is a mutable collection. Okay, this map contains key as string, value as integer. All right. A question from Grisma. Doesn't more parallel task lead to other processes to wait for longer time? That's right. But here, since we are talking about the cluster, if you have like 60 machines and each of the 60 machine is having 4 cores, that means you have parallel 250 tasks can be executed parallelly. All right. If the tasks are short running, then they can finish really quickly, and those 240 machines can be used to execute 240 parallel cores can be used for doing other work. All right. A question from Bintao is, why does collection come from? Right. So here the collection, we are importing, basically this is a class of Scala called collection.mutable.map. As we discussed during we were learning Scala, that there are two kinds of collections. One is mutable and immutable. So we are using the mutable map. All right. So we are just creating a hash map because that'll be easier to check whether a particular word exists in our list or not, in common words or not. Otherwise, we would have to iterate over the list. So for each word, we are checking whether that exists in the common words or not. Had these common words been a really big data, then what will we do instead of this way is we will basically create an RDD out of it and then join it with our, do the left join with our RDD of data, and that would have been far more efficient than this. All right, great. Moving ahead. So basically, level of parallelism is controlled by number of partitions. Okay, so that's the main knob you have. If you have too many partitions, then there'll be a overhead due to each partition. And if you have too less number of partitions, then most of the resources in the network will be idle. All right, now question is, how many default partitions? That's the first question that we face. All right, so let's take a look at this example. Let's take a look at this example. Question is, how many default partitions are there? How many default partitions are there? And here, there is a big file. All right. A question from Rajan is, the common words does not change. Why did you create the maps as a mutable? Because, yeah, I was more comfortable actually here, right? We could, right here, we wanted to add these many values to the map. Okay, so we wanted to append this. So the map which is mutable will be far more efficient at this. Otherwise, on every addition of the key, it'll create a new map and we'll have to access that. so that I created the mutable map so that we could access it. Now moving ahead. All right, now question is how many, it's a very important part, so please pay attention. So question is how many default partitions? That's the question that you have been asking for quite some time. So the default partitions are a function of the underlying storage and also the mode in which you are running. So let's take a look at this file. I'm exiting the Spark shell. Okay. So how many partitions are there? How big is the file? All right. This is the size of the file. Okay. Now, if we just use Python to do this, can we use Python 3? No. Okay. If we use Python to do this, if we divide it by, make it say 0 here, divide by 128, 128 MB, which is these many KBs, which is these many bytes. Okay, so how many blocks? 61.6 blocks. Okay, did something change? Let me see. Oh, it's 61 point. Why is there a difference? 297, right? Ha, there's something wrong, you see. This is interesting. Wow. Okay, there's some precision mistake, that's all. Yeah. Okay, so approximately 62 blocks are going to be there, right? 62. Let's just check. Let's just check how many blocks are there. So you could use HDFS to check the blocks. I'll have to exit. Okay. So this file has how many blocks? If you take a look at this one, connect it to this. So it says 62 blocks. So our hypothesis was right. So as in this file is stored in HDFS. In HDFS, files are broken into blocks and each block has multiple copies. And here, since the block size is 128 MB, so there are 62 blocks. Okay, there are 62 blocks. Now, if we are loading this file, as while if we are in Spark Shell yarn mode, then how many partitions are going to be? If we are loading it in yarn mode, then how many partitions are going to be there? Partitions are going to be equal to the number of blocks in underlying file. All right. So if I just show you this, so you can see 62 partitions. So the number of partitions are decided based on how big this file is. All right. All right. Now let's take a look at the another one. Let's load the data. Let's load the data from in memory. Imagine that we had this array, this in memory array from 1 to 10 lakh, 100,000. Okay, from 1 to 10, 100,000. So let it start. How many partitions will this one have? Anybody? Okay, it might take a bit of time. So here we're saying my RDD dot partitions dot length. So it has two partitions because we are running in the yarn mode. Okay, if we don't run in the yarn mode, the number of partitions are going to be different. Okay, so let's say in the local mode, this is, I'm just going to put it in the local mode. And in the yarn mode is this. Okay, so let's say we are creating an RDD out of 100,000 elements. So how many partitions are going to be there? This one, 4. Okay. Why? Because if you take a look at number of processors or number of cores by using the proc CPU info, there are 4 processors on this machine. All right. Now, question is, what will happen when we start Spark Shell in the yarn mode, but we are loading the data. We are loading the data in memory. So in that case, it is equivalent of number of cores available per machine. Okay, since in our case, when we are running yarn mode, the number of partitions is a function of tasks that can be executed on a particular node, and here it is 2. All right, this we have already checked. So what we learned was, okay, so a good question from David. Is it 4 processors on the actual physical hardware or the number of processes assigned to the virtual server? So whatever is available to us locally, so we have taken it from Amazon, and Amazon has given us 4 processors. And these 4 processors are local and is available locally to us. Whether internally Amazon is doing the virtualization or not, it is up to them. Okay, so how many processors are available to your local process is the number of processors we are talking about when we are running in the local mode. All right. Next question is how do we control parallelism? So we can specify number of partitions in sc.parallelize as second argument or sc.textfile as second argument. Shuffling operations like sort by and partition by, sort by and group by and all of those, partition by, reduce by key, all of those shuffling operations, we call them shuffling because they involve shuffling, accept degree of parallelism in parameter. So repartition or partition by is another function that can be used to repartition your RDD. All right. So what we talked about partitions are the key criterias because they are the key ways of parallelizing the work. And the default values of the parallelism also we talked about. It's a function of number of, now is if you're loading the data from the memory, then the number of partitions are a function of total number of cores available. And if you are loading the data from file system like HDFS, it is basically a function of how many blocks does it have. Okay, the whole thing is the default partitions are optimized for as much as possible for the maximum parallelism possible. Okay, so also if you want to shrink, you could use a function called coils instead of using repartition. Okay, because in repartition you can decrease the number of partitions as well as increase the number of partitions. If you want to shrink to a very large extent, then you could use the coels over the repartition. All right, so label of partitions, we are reading a large amount of data from S3. So example of shrinking is, let's say we are reading the large amount of data from S3, and filter operation is likely to relieve only a tiny fraction of the whole data. Then the result of filter will have same size RDD as parent, but many partitions will be empty, or there'll be very small partition. Now, you can improve the application's performance by using coils, and that's why sometimes you might have to bring down the number of partitions to a small number. Okay, let's say there was a 1 petabyte size of file, and you have applied a filter. Now remaining one will still have so many partitions, even though the data could be tiny fraction of the total number of partitions. Now if you have too many partitions and small data in all, then every operation is going to involve many machines together, and it will be inefficient. Okay, so in those cases it's better to bring down the partitions. Now, next is, while transferring or saving the objects, we need serialization. It comes into play during the large data transfers as well. By default, Spark uses Java's built-in serializer. All right, serialization is converting object into converting an object into something like zeros and ones. There are many serializers available to us. And out of these, protocol buffer comes at the top, then the Kryo, and then the remaining. So these are the fastest serializers available to us. So Spark supports Kryo, and it's a fast and very compact serialization mechanism, but it cannot serialize all of the types of the objects out of the box. Almost all applications can benefit from shifting to Kryo. All you need to do is, in the configuration, when we are initializing a Spark object, we could simply say sc.getConf set spark.serializer, org.apache.spark serializer.cryo serializer. So this way we can say, explicitly specify that use this particular serializer. Okay, so if you have very large objects being transferred, then it's better to use the serializer. All right, likely you have created mm, we have created like customer object, person object, and so on. So you could generally use this serializer. For best performance, register classes with Kryo, and you can simply say sc.getConf and then call register Kryo and call the function, call the class. Okay, whatever class you want to register with Kryo. This is far more, little bit more efficient than using this one. Okay, this one guarantees that your class will be serialized, your objects will be serialized using Kryo. All right, the next part that we talk about often when we are optimizing Spark applications is the memory management. Memory management is basically, we need to understand how the memory is divided. So when we talk about RDDs in the memory and so on, when we are caching something or we are converting in-memory data to an in-memory RDD, so the memory is organized in this way. The various quotas of the various parts of the memory is in this way. So 60% of the total memory given to the Spark, 60% of the total memory given to the Spark is dedicated for RDD. RDD storage, as in when you cache the data, do persist in the memory, and so on. If Spark is not able to fit the data in the memory, the exceeded partitions or the older partitions will be dropped and will be computed on demand. So whenever you're persisting, make sure if the data is huge, use memory and disk. All right. Now, 20% of the total memory is dedicated for temporary buffers, right? Whenever we are sorting the data and so on, we do create temporary arrays, right? And so on. So similarly, Spark also creates these temporary buffers whenever it's doing the processing. So 20% of the total memory is dedicated for sorting and shuffling buffers. All right. Remaining 20% is dedicated for the memory. Okay, remaining 20% is dedicated for the code. Remaining 20% of the memory is dedicated for the code. So 20% for the code, 20% for the temporary arrays or temporary data structures, and 60% is for the RDD. So question is, so the RDDs will be present only during the session's life if it's present in the memory, correct. Only during the process or the job is running. All right. Now, this is basically an important bit to understand the memory. So most of us think that the Spark consumes the entire memory and therefore it won't leave space for others. No, it'll basically whatever memory is allocated to it using executor memory. Remember the executor memory we talked about? Executor memory is basically an argument that you can pass from the command line saying spark submit dash dash executor memory, and using that you could you could you could run you could basically control how much memory you want to give to the Spark application. So it won't overflow any other process, right? So the main parameters of hardware provisioning, the fourth part in the Spark optimization is hardware provisioning. So the main parameters are executors memory, meaning how much big RAM you have, number of cores per executors, and total number of executors and number of disks. When you are trying to optimize Spark applications, the various resources are the main parameters are the various resources constraints, such as how much memory we can give to the executor. More the memory we give to the executor, faster it would do the things, and how many cores are there per executor. If there are more cores, it would handle more partitions on one executor, and how many executors are allowed in one particular machine, and how many disks are there. So basically the application's speed is a function of the memory and the cores. More the memory and more the cores, the application will run faster. If you have huge memory beyond say 64 GB or more, if you have more than 64 GB RAM, what happens is Java garbage collector takes a long time to clear up the memory or check the memory because there's just too many memory addresses. So garbage collector of Java has a concept called garbage collector. What it does is it keeps on observing the memory, and whichever objects are not accessible or are not in use, they are dropped. All right. So Spark is able to achieve something called linear scaling, meaning double the hardware will double the speed. All right. So that was pretty much with respect to the advanced programming. Tomorrow we are going to start with the data frame, or should we start with Spark streaming? Let's just start with Spark streaming tomorrow. All right. So we'll have at least 2 plus 2. I think there'll be at least 4 more classes, 3 to 4 more classes. All right.
Sandeep, I have few questions. Can we discuss offline now or?
Can we discuss it tomorrow? I have a hard stop now.
Sure.
I would love to answer your question.
Okay,
All right. Okay, great. All right. So that's pretty much for today, and we will continue the discussion tomorrow at the same time. Bye-bye. Have a good day. Thank you, everyone. I look forward to see you tomorrow. Thank you, Robin. I'm happy that you found the great session. Bye bye. Have a good day.